Welcome again. I'm Meghamala from Electronics and Communication Department, working as an assistant professor in Institute of Aeronautical Engineering. And coming to the topic, today's presentation is all about user-defined primitives. So let us discuss what are the user-defined primitives, what is the significance in this Verilog. So coming to the first slide here, in Verilog, already we have discussed few primitives which are not confined with this Verilog. But coming to this Verilog, the gate primitives for all the basic gates. Verilog has a gate primitives for all the concerned basic gates. So we know the basic gates and also we know the universal gates as well, AND, NOR, XOR, OR and so on. So this Verilog, it has a primitive already primitive for all the basic gates, and this Verilog, it supports built-in primitive gates modeling. So as this Verilog is concerned with the basic gates, the primitives consist of the basic gates, so it supports the built-in primitive gate modeling. Okay, and coming to the second statement, it states that the gate supports are multi-input, multi-output, tri-state and pull gates. Okay, so already regarding this also we have discussed in the previous session what are the multiple inputs, what are the multiple outputs, and what are the pull-up gates and all. So here the gates also supports for the multiple inputs and single output, and multiple output for single input, and as well as the single input and the single output, and also single input, single output with the control signal. Okay, so the multiple gates are nothing but NAND, OR, XOR, NOR, and whose numbers of inputs are 2 or more and has only one output. So here this particular statement is talking about we have different kinds of gates, right? So all the gates, some gates are having more than one input and some will have only one input, but ultimately the output would be observed as 1. So here it states the same thing. It has only one output, but it has the number of inputs would be 2 or more. Okay, and these user-defined primitives are non-synthesizable. So what does this word non-synthesizable means? Here, like we have one example. This example is all about a wait statement. Okay, in the previous sessions we have discussed few statements, few continuous statements, discrete continuous statement, and also the statements which consist of the keywords. The keywords pertaining to the statements. Okay, so here in order to enhance more what about the synthesizable means, wait statements cannot generate any hardware directly, so it is non-synthesizable statements in VHDL. So in this Verilog descriptional language, we are saying this via wait statement. This wait statement is non-synthesizable. That means what? We cannot generate any hardware directly. So directly any hardware component in between we cannot introduce. So this is nothing but a non-synthesizable, or else it is a non-synthesizable primitive. Okay, not only wait statement, we have few more statements. In the further sections we will discuss what are those non-synthesizable, but in fact to say these are not important to be discussed. Okay, so coming to this user defined primitives. So let us discuss what is a user defined primitives. Just ponder on the definition. Just ponder on the definition. It is a user defined primitives. So here the statement talks about a modeling technique where the user can virtually augment predefined gate primitives by designing and specifying new primitive elements. So what does it mean? It means that the technique where the virtual augment, the user can have the virtual augment predefined gate primitives by designing of this digital circuits or the modules, designing and specifying new primitive elements. So the user itself can design in order to design a particular circuit, a particular any module. If a user want to design any particular module, the user, he will specify new primitive elements. Okay, he will specify. Some primitives are already inbuilt in the Verilog, but few a user can also define by himself. Okay. So the modeling technique where the user can virtually augment predefined primitives. Virtually he can assign virtually the primitives, the gate primitives by designing and specifying. He can design and he can specify a new primitive elements. So such elements are nothing but user defined primitives, UDPs. Okay. So such elements are nothing but the user defined primitives. So these primitives are self-contained and do not instantiate other primitives or modules. So as these are user defined, so these are self-contained. These primitives are self-contained and they do not instantiate or other primitives. As these are self-contained, so they don't have, they don't need to specify the other primitives. And it provides a standard set of primitives, such as the Verilog provides standard set of primitives. So what are those primitives? And, NAND, NOT, OR, NOR as a part of the language. So as a part of the Verilog language, this Verilog primitives are nothing but AND, NAND, NOT, OR and NOR. These are the standard set of primitives. So these are also known as built-in primitives. So as we discussed earlier, Verilog is a very case-sensitive language and it has some built-in primitives. So those built-in primitives are the built-in gate primitives which are present in the Verilog are nothing but AND, NAND, NOT, NOR and OR. Okay, so these are a part of the Verilog HDL language. So I hope you understood what is a user-defined primitives, right? And coming to this slide particularly, the instances of these new UDPs can be used in the same manner as a gate primitives to represent the circuit being modeled. So whatever the circuit that you are modeling, so these UDPs, they use the same manner as used by the gate primitives. So whatever the primitives, user defined primitives, whatever you are using for a modeling of a circuit, so these gate user defined primitives can be used as same as the gate primitives that you have used in the previous one. Okay, so there is no such differences and difficulties to be seen here. They are same, but here the gate primitives are already which are predefined in the Verilog, whereas here user defined primitives will come from the these are the virtual primitives, right? So they are come from the designer. And this technique can reduce the amount of memory and improve simulation performance. So these set the technique which we are using, that means the user defined primitives, the usage of when you are using a user defined some kind of primitives, UDPs. So these UDPs, they can reduce the amount of memory and also they improve the simulation purpose. So this is one of the advantage. Is that the system performance will be increased and also the amount of memory can be reduced. So these are the one of the advantage of usage of UDPs, user defined primitives. Each UDP has exactly one output, which can be one of these states, that is 0, 1 or X. So as I said you, the user defined primitives may have multiple inputs, single output, or a single input, multiple outputs, or pull-ups. Okay, so here this UDP, it has exactly only one output. The user defined primitives, the output of such particular primitives will have only one output, and that output would be either 0, 1 and don't get conditions. Already we have discussed what is X and what is Z. Okay, X is a don't get condition. Okay, and Z is nothing but the high impedance. Sometimes what happens with the help of the control inputs, the output will be observed only with the help of the control inputs. Sometimes without the help of the control input, the output will be observed. So such output, they go high. The high impedance output will be observed. So for that high impedance output, we are denoted with Z. Okay, so the output is observed. It could be either 0 or it could be either 1 or it could be either X. And the tri-state value Z is not supported. So for this tri-state buffers, Z value is not, the high impedance is not supported for such single small gates. Z is not supported. So any input that has a value Z will be treated as X. So here, as I said you, X and Z are almost same. Z is nothing but the high impedance state. X is a don't get condition. So well, in the user defined primitives, when the output you are observing 0 and 1, it is well and fine. 0 is nothing but the false. 1 is nothing but the true. So if you are observing the output, either if it is 0 or 1, it is well and fine. But if in case if you are observing anywhere X, that X you can modify as Z also. So that X would be called as Z also. So any input that has a value Z will be treated as X. So if the input, if there is a high impedance at the input value, so that input could be treated as X also, X as well. Then these two types of behavior can be represented in user-defined primitives. So here in this user-defined primitives, we see the two behavior of the modeling styles. So one is the combinational user-defined primitives, and the second one is sequential user-defined primitives. Okay, so let's see in detail what are these two, combinational and as well as the sequential user-defined primitives. Okay, so a sequential user-defined primitives, it uses the value of its input and the current value of its output to determine the next value of the output. So here, in order to determine the next output, what these primitives will do is the UDP, sequential user defined. The name itself is talking about, it is a sequential user defined primitives. So the sequential user defined primitives, it uses some value. Okay, uses the value of the input and the current value of the output. Some value 0 at the input and the current value output is 1 is observed at the output. So how this output value 1 is observed is, it is just to determine the next output. If for suppose my output 1 is 1, my output, in order to know the output 2, the sequential UDP, it uses the value of the present state input and also the present state output to determine the next value of the output. Okay, next, sequential user defined primitives, it provide an efficient and easy way to model sequential circuits. Okay, you all know what are the sequential and combinational circuits, isn't it? So sequential circuits, we don't have any memory element. Okay, so here the sequential circuit, it has latches such as latches and flip-flops. So the sequential UDPs, sequential user defined primitives, it provides an efficient and easy way to model the sequential circuit. So in order to model, in order to develop the sequential circuits such as latches and flip-flops, basically sequential UDPs are provided. So we all know what are the latches and flip-flops. These latches and flip-flops are nothing but they store the 1 bit of information. These are the storage devices. Okay, registers contains of number of flip-flops. So they store 1 bit of information. Coming to the flip-flops, we have different types of flip-flops. We have discussed in the earlier classes like D, T, master slave and all. So the sequential UDP, it provides an efficient and easy way to model the latches and flip-flops, as these are the sequential circuits. A sequential UDP can model both level sensitive and edge sensitive behavior. This level sensitive and edge sensitive behavior, this you will see in the latches and flip-flops. Okay, level sensitive and the edge sensitive. Level sensitive as well as the edge sensitive. So this sequential UDP models both in level sensitive as well as in the edge sensitive behavior. We will be observe this UDPs, sequential UDPs. And coming to here, the fourth point, the maximum number of inputs to a combinational UDP is 10. So here, as I said you, the user defined primitives may have the multiple input, single output, multiple output, single input, and as well as pull-ups, right? So here, the maximum number of inputs for the module can be 10. So here you can see 10, 0 to 9. So totally 10 bits. So 10 inputs you can consider for the maximum inputs for this combinational UDP is 10. And coming to the last point, the maximum number of inputs of a sequential UDP is limited to 9 because the internal state count is as an input. So the maximum count is limited to 9, isn't it? Because the internal state count is as an input. So there is a limit. There is a limit to consider for the input. Okay, whereas the output is observed only 1, but there is some limit to consider for the input. So that limit, the number of inputs could be limited to only 9 bits. Coming to the syntax. So here in the syntax, we see the UDP begins with reserved word primitive. So in the previous sessions, we have discussed the keywords. Okay, some lexical tokens, right? We have discussed some lexical tokens. Totally, we have 9 lexical tokens where keywords, we have discussed about the keywords, constants, isn't it? And constants, keywords, we have discussed about, constants, keywords, and few totally 11 lexical tokens we have discussed. Okay, so coming to the keywords, we have already discussed the module, end module, begin, end, and so on. Whereas here in user-defined primitives, particularly when it comes to the primitives, we use a word called primitive. So in the previous sections, we have discussed about the module and end module, right? So what is this module? Module is a keyword where this is where to instantiate some program. Module is a basic keyword where we have to use, right? So in this UDPs, instead of this module, we are using primitive. Okay, so here primitive is a reserved word, primitive, and ends with end primitive. In the previous sections, we are starting with the module and ending up with the end module, right? So here we are starting up with the primitive and ending up with the end primitive. Okay, so this is how the syntax follows. So UDP should be defined outside as a module and end module, whereas here primitive and end primitive. So primitive UDP name, output and input. This is nothing but the port list. So this is a port list where we declare the output ports and as well as the input ports. So when you are declaring the ports, always remember that the output port should be declared first and then comes the input port. So similarly, here in this UDP, primitive UDP name, output and as well as the input. And the port declaration. So port declaration, we will declare the input and output ports as well. So registered output, first declared as registered output. And the initial output is nothing but the initial value. So output, what you are observing is initial value. And if you have any table concerning with the gate, table, truth table and end table, if you have a particular truth table for it, then in the syntax you have to mention the table and that table will consist of the truth table and ending up with the end table. So here finally I am ending up my syntax, my particular gate syntax with the end primitive. Okay, so this is very similar kind of thing we have discussed in the earlier as HTL as a Verilog. So primitive UDP representing with the port list and coming up with the instantiation of the inputs and the output. And if you have any truth table pertaining to that particular gate, then the instantiation of that table is been given, mentioned over here. And we are ending up with the statement with the end primitive. So this is how the syntax will be written for all the primitives. Okay, for all the basic primitives, this is how the syntax will be written. And there are some rules to follow in order to write the syntax. So what are those rules? We'll see. So first one is UDP takes only scalar input terminals. So this is also we have discussed in the previous sessions, the module 1. So what are the scalars and what are the vectors? Scalars are nothing but the 1 bit of devices, 1 bit of information we will be observing at the output. Okay, vectors are nothing but there's a combination of bits, right? It's like a recapitulation. Once again I'm discussing what are the scalars and what are the vectors. So if we have a circuit 1 and a circuit 2, okay, so read and write. Okay, we can read the information and also we can write the information. So reading and writing are carried out with the one bit of information, or else 0 or else with 1. But and also we have the registers. R1, sorry, circuit 1, circuit 2. So registers R0, R1, R2. And here this is read and this is write. Circuit 1 and circuit 2. Okay, so here the bits, how many bits are transferring between the two circuits is Z0 to D of 0 is to 2. So D here is nothing but it's a register. Okay, 0 to 2 are nothing but the bits. So totally how many bits? 3 bits of information he's been transferred from the circuit 1 to circuit 2. All together we are transferring it, isn't it? So that's the reason we're calling it as a vector. Whereas here, single one bit is carried out. Reading is done with 1 and writing is done with 0. So the reading or writing, it could be done either is with 0 or 1. So here in the particular UDP rule, the first and foremost rule to follow is the UDP take the scalar input. So the UDP, it will take the scalar input terminal as 1 bit. As it is a scalar, so 1 bit of information it just consider at the input terminal. Next, UDP can have only one scalar output. So as it is a one scalar input it is considered, so it will take the one scalar output. The output terminal always appear first in the terminal list. So in the terminal list, in the port list, the output terminal it should consider, or else it should appear. It must appear, the output must appear as the 1. The output terminal must always appear first in the terminal list. In the list, the output terminal should appear first. In the previous syntax, we have discussed the port list, right? So in the port list, what am I telling? The outputs should be mentioned first, and then comes the input, right? So the same way in the UDP rule, the second rule, it says that in the terminal list, the output must appear first. Okay. Then the third point is the state is a sequential UDP is initialized with an initial statement. So here some initial statement should be initialized first. So the state in the sequential UDP, the initial statement should be initialized first. Then the state table entries can contain zeros or ones or x or z values. Passed to UDP are treated as x values. So here the fourth statement it is telling about a state table entry. It contains the values 0, 1 or x, 0, 1 or x. Only these three will be considered. These three output will be seen. But x values passed to UDP are treated as x values. So in the output basically you may observe 0, 1 or x. If you are observing any z value, then that z values can be observed as x. So here the important thing you have to remember is there is no high impedance value is seen. Okay. When you are observing anyway z value, then that is treated as x value. Okay. Then next, UDPs are defined at the same level as modules. So here, as I said, UDPs are in order to write a syntax, they will follow a keyword called primitive. Okay, likewise, module, they follow a keyword called primitives, and they end up the statement with the end primitives. Likewise, they end up the statement with the end module. So they end up the statements with the end primitives. So here the UDPs are defined at the same level as modules. Next, UDPs are instantiated exactly like gate primitives. So here when you compare the gate primitives and user defined primitives, there is no much difference. Only the same way we will observe, and the way of writing the syntax also observed in the same way. So there is no much difficulty and differences is seen. So the UDPs are instantiated exactly like gate primitives. Okay, and UDPs do not support in-output. So here in the basic module, basic Verilog program, in the gate level or whatever it is, gate level or gate level modeling, or else a behavioral modeling or switch level modeling or circuit level modeling, we see the in-out ports, right? In the port list, we observe, see, in the port list, we observe output ports, input ports, output ports, input ports, and in-out ports in the basic module of AND gate, right? Whereas here in this UDP, you don't see any in-out ports. No in-out port is observed. You see only input and as well as the output ports. So UDP, it do not support in-out ports. It supports only input ports and as well as the output ports. So these are the basic UDP rules to follow in order to write a proper syntax for a particular module or else for a particular circuit. So UDP symbols. So here this Verilog UDP symbols. The Verilog user-defined primitives can be written in the same level as module definition, but never between module and end module, isn't it? The statement clearly talking about we can never write a syntax with module and end module. In place of module and end module, we will be writing the primitive and end primitive. Okay, so in the module definitions, we will be mentioning with the module and end module, whereas in user-defined primitives, we'll be writing a syntax with the word primitive and we are ending up with the end primitive. Okay, next, there can be many input ports but always one output port, and bidirectional ports are not valid. So here we have only one input, they have many inputs, sorry, the input would be many, 0 to 2, but the single output is observed, only the single output is observed, but the bidirectional ports are not allowed. See, we don't see any bidirectional ports is not valid here in the UDP. All port signals have to be scalar as well, which means they have to be 1 bit wide. So as we discussed earlier, all port signals, either it could be 1 bit input ports or as well as the output ports. All the ports they must have to be a scalar. That means 1 bit of wide. No vector is entertained in the user-defined primitives. Only the scalars. They must be in the scalars with 1 bit of wide. And hardware behavior is described as primitive state table that lists out a different possible combinations of inputs and their corresponding output, the table and end table. So here in the previous syntax, you have observed table and end table. So what does this table and end table? This is nothing but the combination. So for example, the combination, the output combinations will be observed and maintained in the particular table. So that particular table we can call it as lookup tables or as truth tables, basically truth tables. So in these tables we will be mentioning the possible outcomes, right? So the combination of inputs. For example, if you consider AND gate, if you considering AND gate, for A and B, output is observed as C. For example, so AB 0 0 0 1 1 0 and 1 1. So AND gate is 0 0 0 1. So this combinations could be mentioned in between the table and as well as the end table. All the corresponding output within can be mentioned within the table and end table can be mentioned in the particular UDP syntax. Then values of input and output signals are indicated using the following symbols. So here there is some particular the symbols, okay, is need to be mentioned when you're writing a particular syntax. So here these are the symbols and the comments. So 0 is nothing but the logic 0, 1 is logic 1, and X is unknown. It could be either logic 0 or logic 1. It is unknown. And question mark is logic 0, 1 or X, it cannot be output of any UDP. So the output logic, it could be 0, 1 or X. See, other than this, if you are observing any output, then we are presenting the symbol as question mark. So it cannot be output of any user defined primitives. And the dash is no change, only allowed in the output of a UDP. So in the output, if you find anywhere dash, it says that there is no change. Okay. Next, AB, change the value from A to B. A or B is either 0, 1 or X. So if you see any change in between A and B, then the comment is nothing but the change in value from A to B or A and B, either 0, 1 or X. And X is nothing but the same as question marks. It indicates any change in the input value. So in the input value, if there is any change, then we are presenting with a symbol like this. And R is same as 0, 1 dash, that is raising edge on output. R is the raising edge on output. F is a falling edge on the input. Sorry, R is a raising edge in the input. Only the input. Raising edge is R. Falling edge at the output is F. Raising edge at the input is R and falling at the output is F. And what is P? P is nothing but potential positive edge on input, either 0 to 1 or 0 to X or X to 1. So it is a potential positive edge. And N is potential falling edge. So P is a potential positive edge at the input, potential falling edge at the output. Okay. So these are some symbols and some comments pertaining to the symbols. We will see all this in the program or the syntax. Coming to the combinational UDP. So we have discussed sequential UDP, right? And as well as in the coming sections, we will discuss in deep what is a sequential user defined primitives as well. So coming to the combinational user defined primitives, in the combinational UDPs, the output state is determined solely as a function of the current input state. So here the output state is determined only, it's solely as a function of the current input state. That means what? Only the current input state, with respect to the current input state, only the output is observed. It's only depends only on the present current input state. Okay. So whenever an input changes state, the UDP is evaluated and one of the state table row is matched. So as I said the output is determined only at the function of the current input state. So if you see any changes that is occurring at the input, then one of the table row it should be matched. That means what? We have to see the changes, or else we have to see the combinations. We have to see the changes where it has occurred, or else what sort of changes have been made. But basically, when it comes to the output, only the particular input change, only we can see the output is only determined the particular input current state of the particular input. The output state is set to the value indicated by the row. So the output, whatever the changes have made to the input, we will be observing the output at the output section, right? So that output state is set to the value indicated by the row. So whatever the row it is matching, so that output is the output state is set to that particular row. And the maximum number of inputs of a combinational UDP is set to 10. So the maximum number of inputs is set to 10, but the limited number of input is set to 9. 9 is limited, but the maximum number of input is 10. Consider the following example, which defines a multiplexer with 2 data inputs, control inputs, but they can only be single output. So here in this combinational UDP, we will see an example. So that example that we are considering a multiplexer. So we know that multiplexer, the output is observed only one output, many input, right? So we see in the earlier classes, in the earlier sessions also, we have discussed different types of multiplexers. 2 by 1, 4 by 1, 16 by 1, and so on. So in the multiplexer, the output is observed only 1, but the input it could be 2, 4, 6, 8, and so on. Based on the selection lines, output is observed. Okay, so in this particular combinational UDP, we will see with the particular syntax multiplexer with a particular example. So the output should always be the first signal in the port list. So this is same like a Verilog syntax, whereas here in the Verilog also the output port in the port list, the output is mentioned first and then comes the input. So here in the same, primitive is a keyword for the user defined primitives. Primitive is a keyword, and here the particular example that I am considering is multiplexer, mux, and here it is a port list. So this port list consists of the output and as well as the input ports. The important thing to remember here in this port list, there is no way of considering in-out port. So there is no in-out port, only it has inputs and as well as the outputs. So primitive, multiplexer, my output, selection lines A and B are the inputs. Done. And output is observed at the out and input is observed at the selection A and B. So this is the instantiation of the input and the output ports with respect. Then coming to the table. Okay, so this particular table is about a selection A and B are the input, output. So for this multiplexer, there is a combination, right? So for here it is 0, 1. See here, you might have observed a question mark, right? What does a question mark says? Question mark says that it cannot be output of any UDP. So if there is no, it could be either 0 or 1 or X. Other than this, if you see any kind of output, then we represent the question mark, right? So in the particular table also, 0, 1, we will observe 1 only for two combinations, right? For 0, 1, 1, and for 1 and for 1, 1, it is 1, and for so 1 is observed for 0, 1 and 1, 1. So we have 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. So for 0, 1, 1 output, and for 1, 1, also 1 output. So for 0, 0 and 1, 0, what happens is here 0, 0 and for 1, 0. So for 1, 0, we are observing that somewhere in the input is, it could be either 0 or 1 or don't care. Okay. So then in that cases, we are observing or else we are mentioning the question mark and we are ending up with the table, end table, and with the syntax as end primitive syntax. So here, this is a text bench. This is a text bench syntax. In this text bench syntax, same like the previous one. When you compare with the Verilog syntax, in the user defined primitive also we have a text bench syntax. For this module test bench, register the selection line and input A and B, and 2:0 is nothing but the delay. Okay, delay with the 2 bits of delay, and wire out and integer I. Okay, just to represent the integer I. Then instantiate the UDPs. Now we have to instantiate the user defined primitives. How? UDPs cannot be instantiated with port name connection. So in order to, when you want to instantiate some keywords or some coefficients, then it says that UDP cannot instantiate with the port name connection. So when you have this port name connection, you cannot instantiate. So here, mux, we are not instantiating now. We are simply writing the syntax mux with the port list, output port, and as well as the input port. And here we are beginning. Okay, we are instantiating first A less than or equals to 0, initializing the program with B less than or equals to 0. And now I have to see in the monitor display what comes. So in the display, it comes with the delay of 2 bits of delay and the time as 2 nanoseconds or 2 bits of delay with some time, nanoseconds, A, B selection and output. This is what we observe in the display. But in order to drive A, B and selection lines, these three are the input lines, right? So in order to drive randomly, not in a sequence wise, in order to drive randomly, what happens is fur will come. The fur is another keyword, isn't it? Keyword, module, end module, begin, end, if and while. These are the keywords, right? So here for is also a keyword that begins with I is equals to 1. So here we are initializing I integer as first one 0. Later on A less than or equals to 1, right? So I less than or equals to 10. Why? Because here my inputs, the maximum input would be 10. So I less than 10, then goes I is equals to I plus 1 begin. So here the randomly, the delays may go randomly, not in a sequence wise, but randomly. That means what? If this is an output, this is an input for bits A and B, my randomly I can observe for 10 bits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So randomly I can see the raising and falling edge. Okay, randomly raising and falling edge we can observe. So R and F can be observed randomly. Why? Because here in the particular question, randomly we are considering the inputs A, B and selection lines. For 0, 0, 0, 1, 1, 0, 1, 1, randomly I am considering. So in the case, I can see at the timing diagram, I can see randomly the rising and the falling edge of the thing, the time delay is being occurred. So here delay A random and delay is exactly here with I less than 10, right? So with some randomly for suppose 1 nanoseconds, and second is for B for 2 nanoseconds. And likewise, if I am considering 10 bits, so for A bit 1 nanosecond, B is for 2 nanosecond, C is for 3, 4 and so on. For 10 nanoseconds, I can select the input selection lines randomly. So this is how I am ending up with N for this for, and this is N for the table, and this is N module for the whole syntax. For the whole module, I am ending up with the N module. So this is all about the combinational UDP. Okay, so here I want to explain this. Here question mark, it indicates a signal can be either 0 or 1. So here the signal can be either 0, that is 1 or 0, or 1 or 1. So X does not matter in deciding the final output. So as I said you, X is a don't care value, so it doesn't matter. It could be, X could be either 0 or 1. Okay, and here the question mark here itself, it's indicating the output. If you're considering a output, if you're getting any X, then that is nothing but it could be either 0 or 1. But at the input side, if you are observing any question mark, the question mark itself indicates that it could be either 0 or 1 or X. Okay, 0 or 1 or X at the input. We are representing it with the question mark. So this is all about the today's presentation. So we have discussed what is user-defined primitives, what are the basic primitives, and how these primitives are helping in order to write syntax for the combinational circuits that you are considering, and not only for the combinational circuits as well as for the sequential circuits, that is in flip-flops and latches. Okay, with how much of delay that you are considering and how to display the delay and the output in the display unit. Also we have discussed, and also the behavior, behavioral modeling, that is nothing but the combinational UDPs and sequential UDPs. So this is about the user-defined primitives. In the coming classes, keenly we will get to know what is a sequential user-defined primitives as well. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.